All right. Okay, we'll go ahead and get started. All right, so this is our 2 o'clock press conference. Welcome to Bennu. So our participants today are Jeff Grossman from NASA headquarters, Dante Lauretta from the University of Arizona, Michael Nolan, also from the University of Arizona, and Amy Simon from NASA Goddard Space Flight Center.
OSIRIS-REx is the third mission in NASA's New Frontiers program. These missions are competed missions and led by principal investigators from the community, and they cost in the range of $1 billion each mission. OSIRIS-REx is the third mission. It joins New Horizons, which is going to encounter a distant Kuiper Belt object, Ultima Thule, on New Year's Day, and Juno, which is currently orbiting Jupiter and studying its atmosphere, and another mission to be announced next summer. It's scheduled to be announced. So that's the New Frontiers program. The New Frontiers program is one component of NASA's planetary mission fleet. These missions range from all stages of development. Some of them are just being developed, others are in primary operations like OSIRIS-REx, and others have completed, like the Dawn mission, and a few others, and they span the whole solar system. These missions are NASA-run, and many of them have international partners, and a few of them shown here are international missions that NASA participates in. You may notice that many of these missions, if you recognize them, are going to the small bodies in our solar system. Small bodies rather than planets or their large moons. Small bodies are bodies that range in size from only a few meters across to hundreds of kilometers, like the largest asteroids. The one that OSIRIS-REx is going to, asteroid Bennu, is about 500 meters across, which is about 3 city blocks in diameter. These bodies are mostly fairly primitive bodies. They never managed to form into large planets, and they tell us many things about the early solar system and other things about our solar system. The small bodies missions are spanning our solar system, exploring it from one end to the other. From out at Ultima Thule, where New Horizons is in the Kuiper Belt, which is about 40 times as far from the sun as the Earth is, to Juno, to Lucy, which will be looking at small bodies that share Jupiter's orbit when it goes out there in the next decade, to a few missions in the main belt of asteroids, including the completed Dawn mission and the upcoming Psyche mission, and several missions that are studying objects in the inner solar system, like OSIRIS-REx. And the great thing about studying an inner solar system, a near-Earth asteroid, like Bennu, is that it's accessible, and that enables OSIRIS-REx to do something great, which is to bring a sample back to Earth. The topics that there are many problems that these missions are attempting to solve. These range from how our solar system formed, to how the solar system got to be the way it is, to what the properties and processes in the solar system are now, to the hazards and resources that asteroids pose to Earth or provide to explorers. And critically for OSIRIS-REx, one of the things we hope to learn is about the inventory of volatile elements and organic matter that may be present in the solar system. And OSIRIS-REx, as you can see on this chart, has a lot of its potential to answer questions in questions like that. And I think what we've now know, and what we'll hear in this press conference, is that we've gone to the right place to answer these questions, and that Bennu is proving to be just the asteroid we hoped it would be, and now we'll find out why.
Thank you, Jeff. Can I have that? Thank you. So I'm Dante Lauretta, professor of planetary science at the University of Arizona and the principal investigator for the OSIRIS-REx mission, and also very excited to be here today. So thank you for this opportunity. So we are here. We have arrived at Bennu. Arrival was officially December 3rd of 2018, and that was a morning I woke up and saw an event on my calendar that I put there a decade ago. So it was truly a great day for us. And a lot of the uncertainty has been removed about this mission, right? One of the things that's characteristic of OSIRIS-REx is that we're going to a target that we've only seen through our telescopes. And we're using that telescopic knowledge to design the mission and understand the risk posture. But really, we were going to a new world, and we were going to reveal that world and then assess in this early campaign of the mission the challenges that lie ahead. So here you can see so far the best resolution image of the asteroid that we've obtained so far. This was right before the arrival on December 2nd, when we were using our Polycam high-resolution imager that was built at the University of Arizona to get 33 centimeter per pixel images, and then this is a multi-image mosaic that's stitched together to show the overall asteroid texture. And there's a couple really interesting features here. We'll hear more about the shape when Mike Nolan gets up and talks to us, but we did relatively accurately predict the shape of the object. We are looking at a bouldery surface, remembering that this is a sample return mission. We are going to have to send our spacecraft down to make a brief 5-second touch and go contact with the asteroid to collect material on the order of centimeter sized particles. We are seeing some basins or depressions, and we're discussing the nature of those and the origin of those. Some of those look like traditional impact craters. Others may be expressions of the interior structure or the evolution of the asteroid. So there's a lot of excitement here, and I just want to emphasize these are really early days in the mission. This is kind of our first look at the asteroid, and we have a long time to explore this and make the critical operational decisions about where to go on the asteroid surface to get that sample. So the good news is when you're working with NASA on a mission like this, you like to have very clear and well-defined mission success criteria, and we made sure that there would be no doubt as to whether or not OSIRIS-REx was a success. And we're proud to announce today that the first mission success criterion has been achieved. We have rendezvoused with asteroid Bennu, and we have begun our exploration of this fascinating small world. The next one is probably the grand challenge of the mission, which is to contact the surface of the asteroid and collect that sample. And then, of course, the mission culminates in 2023 with the safe return of that material to Earth, ultimate delivery to the NASA Johnson Space Center and to the Astromaterials Curation Facility, where it will then become available worldwide to researchers across the planet. We have a phenomenal payload suite. Our scientific instruments are truly world-class. In addition to the camera system that was provided by the University of Arizona, I showed you the Polycam imagery from right at the end of our approach phase. We also have MapCam data and SamCam. MapCam is our global mapper, and it has the color filters, and we'll be showing some color imaging data. And then SamCam is there to document the sample collection activity. The Goddard Space Flight Center and my colleague, Dr. Amy Simon, is the deputy instrument scientist for the visible and infrared spectrometer. And we'll be hearing some more information about what that instrument has detected. The Arizona State University provided the OSIRIS-REx thermal emission spectrometer, the OTIS instrument, which is right here. And our Canadian Space Agency partners provided the OSIRIS-REx laser altimeter, which did just get its first data a few days ago when we were entered preliminary survey and started our North Polar Pass, and we're still actually assessing the nature of that information and processing that. And then we're also really proud to fly a student collaboration experiment. That's the Regolith X-ray imaging spectrometer, the Rexus instrument from students at MIT and Harvard University to look at X-ray fluorescence from the surface and tell us about the elements that are there. And they're also still in checkout and calibration phase, and we don't have any information about the nature of the asteroid from them yet. So with that, I'm going to hand it over to Dr. Simon to tell us about the spectral analysis results from the mission.
Okay, so are we on?
Take this one. Put on.
Okay, so as Dante said, we're all extremely excited to be here and to finally be at the asteroid. And I'm representing the two spectrometer instruments today. And so that's OVIRS, the visible and infrared spectrometer, and OTES, the thermal emission spectrometer. And the thing to remember about both of these instruments is that they're not imagers. They're point spectrometers. So whatever spot we're looking at on the surface, we're seeing we're not making an image, we're seeing the spectrum of everything in that spot at the same time. And so we started our observations on approach to the asteroid on November 2nd, so about 200 kilometers away is when we got our first look at the asteroid. So for O viewers, this is what we saw. We have this beautiful spectrum, and you can see that the asteroid does not fill our field of view. It only filled about 45% of the field of view, actually. And so we were seeing the entire surface on that side of the asteroid plus dark space around it all at the same time. And even so, we were able to make our first detection of a real spectral signature that relates to the asteroid's surface, and that's the feature you see here at 2.7 microns. And if you're wondering what that feature is, it's one of the things we were hoping to find. So we're super excited and happy to say that we saw the evidence of hydrated minerals on the surface of Bennu. We saw this in every single one of the spectra we have taken to date. And so that means we're seeing this widespread hydrated minerals throughout the surface, which is really great news. It's very similar to what we see in meteorites that have been analyzed here on Earth in the laboratory. And once we got a little bit closer, we were able to use OTES, which has a bigger field of view, and also get a strong signal. And again, they also see evidence of hydrated minerals on the surface. So this is both spectrometers working in concert to confirm what each other is seeing, and we're seeing great matches with some of the meteorites. And so why is this important? And that's because to get hydrated minerals in the first place, to get clays, you have to have water interacting with regular minerals. Once you've made the clays, they can actually bond and store some of that water in there and make it water bearing. So these hydrated minerals have evidence of liquid water in Bennu's past. So this is really big news, and this is a great surprise. So with that, I'm going to pass it over to Mike Nolan to talk about the shape model.
All right, so I'm Mike Nolan. I'm the science team chief, and I'm at University of Arizona, and I conducted the shape model. So in 1999, almost 20 years ago, I was a junior scientist at the Arecibo Observatory in Arecibo, Puerto Rico, working at this very large telescope. And one of the ideas that we had going into this was that we might be able to make observations that would someday be used in planning space missions. And so here's the data I took. On the left are the actual radar image data from Arecibo. You can see they're noisy and speckly, but Bennu was 3 million kilometers away, so that's still pretty good. And from that, we made, using a computer model, we made the shape model on the right, which you can see up here in the table too. We made the shape model. It's sort of a lumpy round thing, and let's see if we can get that play again. We did see one sort of obvious boulder feature and said that we thought that was probably 10 or 20 meters across, but we couldn't really see any below that. The size of our pixels here is about 15 meters. But so we knew there was one big one, and we got an overall shape, and people always ask me, how much do you believe this shape? And I said, well, I believe that boulder's there. I think the sizes are about right. Some of those little wiggly details I'm not so sure about. So then we got our ground-based model. So on the right is the model that I just showed you that we made, and on the left is the actual imagery that we got. And so as far as I can tell, every single one of these little features on here has some meaningful signature on the asteroid. The model works remarkably well. It's missing some of the surface detail because it was a little coarser than of course we would have liked. You'd always like to do better. But everything in this model is you can see in the fixture. So there's our little bump, and there's a boulder. Even this smaller boulder is revealed there. This little valley you can see in the images. So it worked remarkably well, which is important because we made a lot of our decisions about how to go forward with this mission based on this model. And so the fact, and people say, "Are you sure?" I said, "I'm as sure as I can be. Let's go do it." And we went and did it, and yep, it really worked. So now we have, of course, now that we're there, we're using images to make a new shape model. And so on the right, you can see the new shape model of Bennu made from those images on the left. And so it's got a lot more detail. It's a little more, we have the models here. You can see that the real asteroid is a little more squashed, perhaps, than the model we made. And in fact, that was the one thing I said that really might be true. When you look at what radar can do, it might be a little different. But it worked remarkably well, and what that means is that pretty much all of those decisions we made about how to go forward are really going to be, we're accurate enough that we can really use them and say, yes, we can, that's really what Bennu looks like, and now let's go get our sample.
Thank you. So before I go on, let me just say that the findings that Amy talked about are really, really exciting for us. I mean, we targeted Bennu precisely because we thought it had water-bearing minerals, and by analogy with the carbonaceous chondrite meteorites that we've been studying, organic material. That still remains to be seen. We have not detected the organics, but it definitely looks like we've gone to the right place. Both the OSIRIS instrument with the detection of the 2.7 micron feature and the OTIS instrument with the spectral matches to the CI and CM carbonaceous chondrites really is exciting. I mean, I know when Amy and Dr. Vicki Hamilton, who leads the spectral analysis working group, first called me with the 2.7 micron results, we were so excited, and it just was everything we'd hoped had come to pass. Very early in the mission, we had found out that in fact Bennu is going to be able to provide the type of material that we want to return and get back into our laboratories to answer these fundamental questions about whether these carbonaceous asteroids might have delivered these compounds to the surface of the early Earth and led to habitability and maybe even the origin of life. So let me go over a couple other results. I talked about the MapCam. That's the color imager. It has 4 different bandpass filters in the red, green, blue, and infrared. And when we're looking at Bennu, one of the other things that struck us early on when some of the images were coming in from Polycam, like the one that we see over here on the right, these are at really low phase angles, which basically means that the sun was kind of right behind us, so there's very little shadows. And all of those color variations or contrast variations that you see on the surface are real. So we're seeing a lot of different kinds of reflectivity in the surface material, probably related to the composition. So we are seeing a fair bit of compositional diversity, which wasn't something necessarily that we would have predicted or expected from the ground-based data. In fact, as we had watched Bennu rotate in various telescopes and with spectrometers attached to them, we didn't see a lot of spectral variation or even reflectance variation. So to see this wide range of reflectance properties is really surprising. And we see it in the color. So over there on the left is a MapCam red, green, blue color composite image. You can see the dark spots showing up really nicely. Bennu is bluish. We had thought that from the beginning. It's a B-type asteroid, and that means it reflects more blue light than red light, and we are seeing that color variation that we expected showing up in the ratios. And there'll be more information about the implications of the color variations during our presentations tomorrow morning. We also care a lot about the thermal properties of the asteroid. So we tied, Mike mentioned, thinking about planning a spacecraft mission based on his data processing. Well, a lot of the safety of the spacecraft and how we designed the spacecraft was based on that information. And we took his shape model along with observations made by the Spitzer Space Telescope and came up with what we thought the thermal profile would be of the asteroid. And then you design the spacecraft hardware to be able to survive those thermal regimes, particularly during the sample acquisition event. And what the graphs over there on the right show is the OSIRIS data at 4 microns, so out in the infrared part of that instrument's capabilities, compared to what we predicted the thermal flux or the infrared radiation coming off the surface of the asteroid would be based on the ground-based shape model. And then you see the similar kind of plot down below. This is the OTES 14 micron channel, so farther out into the mid-infrared, where you're really getting a lot of the thermal emission or heat flux off the surface of the asteroid. Those are the blue circles compared to the prediction using the asteroid shape model in the red curve. So the good news is, again, the shape model, Mike and his team at Arecibo and also using Goldstone Planetary Radar System in California really nailed it. So the planning that we did, the design of the spacecraft, the observation profile, they're all spot on. We are ready to go. There is nothing about this asteroid that is going to prevent us moving forward into the intensive science mapping campaign that we have planned for 2019. And then I just want to highlight a couple of the really interesting geologic features. So I would say, Mike, the one thing was that 10-meter size boulder turned out to be substantially larger, on the order of 50 meters. And there's a fair number of 10-meter size boulders, and the boulder geology is fascinating. I definitely can't go into all of it here. This is one area that it looks like it's a disaggregated breccia, and that's something I'll talk about during my presentation tomorrow. But we're looking at a wide variety of the reflectance variations, even as we get down into the tens of centimeter scales. We're seeing clasts or rocks that look very bright, connected to some that are very dark, and then when we look at a feature like this, they look like they're maybe falling apart due to some kind of thermal stresses or fracturing or weathering pattern. We do see rocks that appear to be outcrops, that they're some just tip of the iceberg reflection of something that appears to extend much deeper down into the interior of the asteroid, like this feature here. And it's got a lot of linear features associated with it, which also may be due to thermal stressing and fracturing on the asteroid surface. And then we also see these perched boulders. There's some that, like especially the big one that we even saw in the ground-based radar data, and several others that are 10 meters or larger, 10 to 50 meter size range, and they appear to just be resting right on top of the asteroid surface, like they fell back on or something weathered around them and left them exposed. So the bottom line is, this is an interesting world from a geologic perspective. There's a lot going on here in terms of processes on the surface of the asteroid, modification of the material, and that's something we want to get a good handle on, because as we're going through our sample site selection process, we want to understand where do we have the best opportunity to get this most primitive, oldest material from the dawn of the solar system, and where might we get material that would tell us about the geology of the asteroid and the processing that happens on the surfaces of the asteroid. In the best world, we would get both kinds of material or multiple kinds of material depending on what we see on the surface of this asteroid. And then we were starting to look at where we might be able to go get a sample. I know it's very early days here, but as the PI of the mission, I have to think about that second mission success criteria: safely contact the asteroid surface and collect a sample. And it's a little early, but we are seeing these basins and possible impact craters. This one here, it's over here on the left of the image, is about 20 meters in diameter, which is of order of our navigation capability in terms of accurate targeting a location on the asteroid surface. And we are seeing the finest grain material seeming to accumulate in these low basins here. We haven't mapped the entire asteroid surface yet. We've only been at this for a week, and our team is going through this in a very systematic manner. And this is just the preliminary survey data. When we get to the detailed survey next year, when we're in our site selection campaign, we're going to get about a factor of 6 to 7 times better resolution. So right now we're at 33 centimeters per pixel. When we do the global mapping campaign, what we call our baseball diamond, which refers to the different look angles so that we can get stereo imaging and different shadowing features, we'll be getting down to 5 centimeter per pixel resolution. And then once we've got regions of interest selected on the asteroid surface and we get into this reconnaissance phase, we'll be doing low altitude flyovers of potential sample sites, and we'll be getting sub-centimeter per pixel resolution of these regions of interest and potential sample sites. So we are going to take our time. Right now we're still in the navigation campaign of the mission, which means we're learning to fly. One of the big challenges of OSIRIS-REx is accurate navigation of the spacecraft in this microgravity environment. It's more akin to docking than it is to landing when we go in to get that sample. So a lot of the expertise from NASA and from our partners at Lockheed Martin that relate to space situational awareness or rendezvous with a target in Earth orbit like the International Space Station come into play with OSIRIS-REx. So we want to take our time and make sure that we know how to fly, and that's what the navigation campaign is about. We're getting quick early look data in preliminary survey. We're planning an orbital insertion in orbit A, and we actually do have an estimate on the mass, and I'll be talking about that in the presentation tomorrow, as well as our radio science team and Dan Shear's presentation. But in orbit, and that'll be a record for the smallest object ever orbited by a spacecraft, we'll really transition over to what we call landmark tracking optical navigation, where we look at features on the surface of the asteroid and use that to determine the spacecraft position. So it really won't be till the end of February where the science campaign, what we call the site selection campaign of the mission starts, and the science team is kind of in charge of where the spacecraft is pointing and the data that we're collecting, processing all of that information. And once even we have a site, which we anticipate by the end of 2019, we're going to spend about 6 months designing the descent down to the asteroid surface and rehearsing various approaches to make sure we do it in a safe and systematic manner so that we go and get that sample approximately July of 2020. We're confident in mission success. One of the other things we did along those lines in terms of our readiness for TAG, or the touch and go sample acquisition event, is to extend the robotic arm. That's called TAG-SAM, the touch and go sample acquisition mechanism that was provided by our team members at Lockheed Martin. And we got it out in front of the SAMCAM, and the image that you see over here on the right is an in-flight image. One of my favorite images because you can actually see sunlight passing through the filter screen. This is basically an air filter, and I call TAGSAM a space vacuum cleaner. We're actually going to blow high purity nitrogen down into the regolith of the asteroid and push it up into this filter. And the fact that we can see the shadow of the filter screen on the inner portion of the TAGSAM makes me look forward to that day in 2020 when we take the same image after the sample acquisition event and we can see outlines of grains there. So fingers crossed, after sample acquisition, these images from SAMCAM will help us verify successful sampling, and then we can start thinking about stowing that in the sample return capsule and bringing it back to Earth, which will occur in September of 2023. So this is kind of our report card. For those of you who don't know, the name OSIRIS-REx, as I like to say, is an awesome acronym that describes the scientific objectives of the mission. So the first one, origins. Looks like we've got to the target that is like our most volatile and organic-rich carbonaceous meteorites. From the spectral interpretation, we thought there would be clay minerals on the surface of this asteroid, and as Amy said, that we have found both in OVIRS and OTIS data, strong, convincing evidence that the surface is dominated by these clay minerals. From the resource identification and kind of the feed forward to asteroid mining, Bennu appears to be a very water-rich target, and water is the most interesting and possibly lucrative commodity that you would mine from an asteroid, so you could process it into rocket fuel in situ in space. And from security, which relates to the fact that Bennu is a potentially hazardous asteroid with a non-negligible probability of impacting the Earth well into the 22nd century, we have already, from our initial preliminary survey flybys, characterized the mass. Combining that with the shape model, we have a constraint on the asteroid density, and then the orbit of the asteroid, and folding all of that information into predicting the likelihood of an Earth impact. That's still work to go as we move forward. I would say the one area that we were surprised by the asteroid and where the challenge ahead lies is that we were working towards one boulder on the order of 10 meters. We've got hundreds of boulders on the order of 10 meters. The average grain size was predicted to be on the centimeter size scale. That's still to be determined as we get into the higher resolution imaging campaigns. But certainly it's a little more rugged of an environment than we had expected based on our mission planning and the ground-based observational data analysis. So I will leave you there with this portrait of asteroid Bennu, and I think we're ready to move on.
Okay, so questions, yep. Please remember to state your name and affiliation.
Hi, Sid Perkins. I'm a freelancer. And related to your last point, in looking at the population distribution of boulders and sizes on the surface, is that what you would expect? Are you seeing something of a Brazil nut effect where the big stuff rises and the small things kind of settle? Or what can you say about that versus your expectations, if you had any?
Right. Well, certainly our expectation was that there would not be as many boulders of this size scale on the surface of the asteroid. So that is the big surprise so far that we've encountered with the asteroid. In terms of what's causing the boulder distribution, it looks like there's multiple processes at work here. And like I said, it's really early days. We've literally had 7 days to think about it, plus getting ready for all these events that are going on here at the AGU. So I almost say come to the talks tomorrow, because we've got 3 different presentations on boulders and geology, plus posters on Wednesday afternoon. There's a lot going on to explain the boulder distribution and their morphologies on the surface of this asteroid.
Seth Bornstein, AP. 2 quick questions. First, the mass of Bennu, if you can give us that. And second, have you seen anything that's different than, for example, Ceres and Vesta, which would be the ones you'd be compared to in terms of past missions? Is there something that you've seen on Bennu that we haven't seen on any other asteroid yet?
Sure. So in terms of the mass of the asteroid, we work in units called GM, which is the gravitational coefficient times the mass of the object. From the ground, we had predicted about a value of 5.2. And we're seeing a little lower than that, around 4.9. Probably a better value is the density. And the density is coming in at just under 1,200 kilograms per cubic meter, remembering that your average rock is around 3,000. So it's got a lower density than even these carbonaceous chondrite meteorites, which tells us that it probably is made of these hydrated minerals, which are generally low density, but it's also got some porosity or cave-like structures in its interior, to the tune of maybe 40% of that asteroid may be void space in the interior to get down to such a low density. In terms of comparison to Vesta and Ceres, it's really not fair because this would be a boulder on the surface of those objects. Those are really planetary scale bodies, and especially something like Vesta, which has gone through planetary differentiation, core formation, volcanism on its surface. Bennu is a totally different creature compared to those objects. It really looks like a pile of rubble in the sense that it probably originated from a larger asteroid. We have some working hypotheses that it came from a much larger body on the order of 100 kilometers in diameter, and that was probably shattered in a catastrophic collision on the order of 800 million to a billion years ago. And Bennu is just an accumulation of rubble from that event. It's very different than Vesta, maybe more like Ceres in the fact that it's got these water-rich minerals and so on. But again, Ceres is kind of a planetary scale object, and you're going to have a lot more active geology and surface expressions and cryovolcanism and things like that you would never expect to see on Bennu.
Harvey Lyford, freelance. I'm wondering, first of all, whether this is the smallest object in space that we've orbited with a spacecraft. And secondly, how much gravity can it have for you to have a stable orbit around it? I wonder how that works.
Sure. So it will be the smallest object ever orbited by a spacecraft. That will happen on New Year's Eve of this year, so pay attention for that exciting event. And the acceleration due to gravity at the surface of the asteroid is estimated at about 10 micro-Gs. So 1 G is the average acceleration at the surface of the Earth. So we are 1 divided by 100,000th times that. So it is a really low gravity environment. And I mentioned the navigation challenge, and that's the reason why. You've got a gravitational force on the spacecraft that is comparable to solar radiation pressure, as well as outgassing from the spacecraft or even thermal radiation from the asteroid. So that's why the navigation team gets 2 months to learn how to fly as they get into orbit at the end of the year.
Alex Witzy with Nature, just sticking with the Dante theme. Wanted to ask you to talk more about the grain sizes. You can sample only up to 2 centimeters. You've got a very, very rugged look here, as you pointed out. You're noting these basins as places with the small grain material to maybe try and sample. How much are you worried about that 2 centimeter sampling limit?
Well, I don't worry about things that are out of my control, right? So we did everything we could to plan this mission. I am confident we're going to find some fine-grained regions. The challenge will be how large they are and what that means for our navigation accuracy as we go in to get the spacecraft precisely targeted to the location that we want on the surface of the asteroid. There's an interesting puzzle going on here because one of the key pieces of evidence for the average grain size was a parameter we call thermal inertia, which basically tells you how fast the asteroid surface heats up and how fast it cools off. And usually lower thermal inertias correspond to smaller grain sizes. So that's one of the reasons we estimated the average grain size on the order of 1 or 2 centimeters. We're still seeing that low thermal inertia. I didn't go into it on the thermal plot, but when we looked at that profile, the thermal curve as Bennu rotates, it's very consistent with the thermal inertia that we estimated from the ground. So there's some physics that we need to go back and take a look at and see, and maybe there still is that fine-grained material. There's still plenty of unresolved regions on the asteroid surface, and it may be dominated by centimeter-scale particles. Remembering our pixel is 33 centimeters at this point, so we don't know what's happening inside those single pixel regions. And as a point of reference, the pixel size is just about the same size as the diameter of the TAG-SAM head. So we have to get TAG-SAM to 1 pixel on this image, and there's plenty of regions that we don't know what's happening at that scale. So that's why we have the year ahead of us to do the detailed mapping and ultimately the high-resolution reconnaissance.
Christoph Seidler, Spiegel Online. Dante, you mentioned that it would be unfair to compare Bennu to Ceres, for example, or Vesta. Can you compare it to Ryugu, the asteroid that Hayabusa 2 is currently at, just to have a vague idea how these are similar or different?
Does anybody want to take that? I've been answering a lot of questions. Anybody else?
Well, I guess at least from the spectral point of view, we can say that based on Ryugu, we weren't expecting to see these hydrated minerals so easily from so far away. So that was actually a big surprise that it was such a strong signal immediately without even a full field of view filled in. So I think we probably do have more hydrated minerals than they do. We'll know a lot more once we enter that science mapping phase and can look at variations on the surface and get better ideas of where things are concentrated.
I'd say one other thing is, so we knew Bennu looked like this we've known Bennu's looked like this for a long time, but we didn't know Ryugu looked like it does. And so when we saw those images of Ryugu, we were looking at those and say, well, Bennu's likely, since overall they look kind of the same, we expect maybe they'll look the same in detail. And then when they're actually so different, that was even more exciting, that you have these things that are superficially very similar, but then in detail they're really quite different. And so that's another exciting aspect of going forward here.
I believe we have a question on the chat.
We have a question from.
Go again. Is it on?
Hello. Okay, cool. We're on. I have a question from Vikas Nath with hotpoprobot.com. The question is, currently Bennu is the second most hazardous object in terms of possible collision with Earth according to NASA's Palermo Technical Hazard Scale. How will the mission help us in improving the risk index associated with asteroid Bennu?
So one of the big uncertainties in the trajectory of the asteroid is a phenomenon called the Yarkovsky effect. And the Yarkovsky effect relates to the fact that the asteroid gets heated up by the sunlight, and then as it rotates into its afternoon and its evening, it releases that energy back out into space as heat. And it's a retrograde rotator, which means its afternoon is in the direction that it's moving on its orbit. So that emission of heat acts like a thruster and applies the brakes and slows the asteroid's orbital velocity down, therefore shrinking the semi-major axis of its orbit. We're going to study that phenomena in unprecedented detail, and we're going to do it in two directions, from the top down and the bottom up. Mike talked about the radar data starting in 1999. We got even better data in 2005, and then in 2011, we were able to range to the asteroid. We didn't get the imaging resolution, but we were able to get its position relative to the Earth. And because of that 12-year arc, we actually measured the Yarkovsky effect in a change in the asteroid's orbit. And then we combined that with Spitzer Space Telescope observations to get the thermal emission, and that was how we got that asteroid mass estimate to begin with. So now we're going to be able to extend the baseline from 1999 to 2011 all the way to the end of our encounter in 2021. So we'll have 22 years of tracking on the asteroid's orbit, and that'll improve our understanding of how much the semi-major axis is changing as a result of this phenomena. But in addition, because we're going to get this phenomenal 5-centimeter resolution global shape model, and we're going to get the thermal emission from the Otis instrument, we're going to be able to evaluate the Yarkovsky effect from first principles. Do we understand the physics of thermal radiation and how it changes the asteroid's orbit? And that'll shrink the uncertainty, and therefore the impact probability will change. Don't know if it'll go up or down, but it'll change as a result of that improved knowledge.
I'd also like to add that knowledge can be then applied to other asteroids, that even ones that we haven't yet discovered, which may prove to be hazardous, and it'll help understand the hazards posed by many asteroids.
Great. Do we have any other questions from reporters in the room?
I've got a really stupid question. What's to say that isn't just a giant chunk of impact breccia from a giant collision that just sort of came together? It hasn't changed.
You want to
since
answer that?
time.
No, that one's on.
Okay, how do we know it's not an impact breccia? It may be an impact breccia. I mean, it is, we expect a pile of rubble that coalesced after a catastrophic disruptive impact in the main asteroid belt hundreds of millions of years ago. And in fact, when I showed you that disaggregated assemblage that looked like it was kind of breaking down in situ, there's very different reflectivities there. So it's definitely a pile of rubble, and whether or not it originated an impact remains to be seen. But that's okay, right? So there's nothing wrong with that.
Seth Borenstein again from AP. Just the bottom right, the bulge that you saw, Michael, decades ago. Is that the 50-meter boulder you're talking about?
Yes.
And how big is the opposite one?
The opposite one, as I recall, it's about the same size around, but it's not as tall. So it's more like 20 tall, roughly.
And is there a good? How do you describe this shape? I mean, is there something similar in people's everyday life that this looks like to you?
Well, I mean, to first order, it's round. But I think of it as sort of two cones sitting on top of each other. That's sort of the way I think about it. Here's a cone and there's a cone, and with the ridge in the middle. That's the overall shape. And we think it's a round thing where the spin has basically formed this big bulge around the equator.
Okay, it's because it's not quite that round. I mean, it's that bulgy.
You start with something round, and then as it spins up, the bits at the equator kind of move out, and that's sort of how we think of it as we think of it as looking that way, and also most like as actually having formed that way.
Yeah, I'd say the shape is a really interesting question right now because we thought it was related to the spin state and material migrating down to the pole, but we had the question earlier about the comparison to Ryugu. Ryugu is spinning much slower by a factor of about 2, and it has a more pronounced ridge, a much sharper peak, and so that is counterintuitive to the rotation state model unless there's been changes in the rotation state of those two asteroids. So I would say the team is having a field day right now because it's an asteroid geologist's dream to have a mystery like this to go and solve. So there's people throwing out all kinds of ideas about how these shapes and how these ridges form. So I would say stay tuned because I think the active debate is going to go on here.
And just numbers of the distance from Earth, and the spin rate for us, please.
So the Bennu is on a eccentric orbit that gets almost out to the orbit of Mars and actually comes inside the orbit of the Earth, so it's an Earth-crossing asteroid. It does a close approach to the Earth every 1.2 years. I believe we have a one-way light time on the order of 7 minutes right now. So that's how we normally measure distance, is how long it takes the signal to leave the Earth and get to the spacecraft and then come back. The spin state is rotating once every 4.3 hours, and we actually know it to something like 10 decimal places, but that's probably good enough for this.
Okay, I think we have some questions on the chat.
Yeah, we have a few questions. The first one is from Lisa Grossman with Science News. The question is, does Bennu look more or less bouldery than Ryugu? How did you feel? Also, how did you feel when you first saw Bennu up close?
You want to take the boulder question?
I'd say offhand, the largest boulders on Bennu are comparatively smaller than the largest boulders on Bennu, and that things scale pretty well. And that's actually in one of the posters that you'll see on Wednesday. That the actual it's less bouldery, but they're comparable in some pretty straightforward ways. And there's a whole presentation of that on Wednesday.
And how did you feel when we first saw Bennu? So I was pretty excited.
Cool.
It was like, hey, we're there, and we have an awesome asteroid to explore. I mean, it's a dream come true, and it's an honor, and I don't want to, and a privilege to be able to lead a program like this for NASA and for the United States and really for the world. And we can't wait to spend the next year mapping this asteroid. It really is the culmination of a decade and a half of work on my part and this team, which has worked together for years and years and years. Just an amazing group of people. This is obviously a very small representation of the hundreds to thousands of people who have worked hard to make this mission a success. And I'm really proud of everybody and all the work that we've done to get here. So we have an amazing spacecraft with a world-class suite of instruments and a fascinating world to explore, and all of that rushed into my mind as I got those first images of Bennu.
Do you have another one on the chat?
Yes. We have a question from Dan Bamberger, a freelancer. The radar modeling for Ryugu didn't show the equatorial ridge, while Bennu's shape was known better. Still, the actual shape is more squashed at the poles. How reliable are radar shapes in general?
So we didn't have a radar shape model of Ryugu. We actually tried, but for various reasons, mostly including funding, we weren't able to get that shape model. I think that was in the early 2000s, whereas we had the radar shape model of Bennu. And actually, specifically knowing the squash, that was our biggest known uncertainty, was how squashed it would be. Mm-hmm. And it's well within the uncertainties we estimated. So that's why Ryugu didn't come out the same, is because we didn't actually have the model to start with.
Okay, one more question from Leah Crane with New Scientist. Do we have any ideas of why Bennu might have so much water?
Sure, I'll take that one. So we think that Bennu, the mineralogy on the asteroid formed basically at the dawn of the solar system over 4.5 billion years ago, when material was accreting from the protoplanetary disk, and the mineralogy is a remnant of that early phase. So as I've mentioned several times at this event, the asteroid is a fragment of a much larger body that originated in the main asteroid belt. And that body, when it formed, probably accreted what we would say anhydrous or dry minerals along with ice particles. And then very early, within the first 5 to 10 million years of the formation of that asteroid, that ice heated up and melted and then created like a hydrothermal system in the interior of the asteroid, and that hot fluid reacted with the anhydrous minerals and formed the clays, and that is still preserved to this day. So that's one of the most exciting parts of studying samples like this, is that you're actually looking at a rock that's 4.5 billion years old, that's older than the Earth, that's older than anything that anybody could possibly touch or study, and you're peering back to the dawn of the solar system and trying to understand the chemical processes that played out that led to the Earth being the habitable world that it is today.
Thank you.
Great. Well, I think we have time for one more.
So to follow up with that, the idea that you've got hydrated minerals, the source of that water was not likely impacts with comets later, or how much could that have been a contributor to your hydration, or is it pretty firmly understood or expected that this was proto solar system?
It's an interesting question, especially your reference to comets. One of the things that we've learned as planetary exploration has rolled out, and especially another NASA mission, a previous NASA mission called the Stardust mission, actually went to the coma of a comet and brought back samples of that material. And one of the things we learned from that is that asteroids and comets are not like two distinctly different kinds of populations. There's kind of this continuum where you have really dry, rocky, and metallic stuff, and on the other end you have nearly pure icy bodies, and then you kind of can get any ratio of mixtures between the ice and rock in between there. So Bennu probably was, at least the parent asteroid that Bennu came from, was comet-like at some point in its early history, and that it was a combination of rocky, metallic, icy, and organic material, and then all of that kind of accreted together, and you had some limited geology taking place to establish the minerals that we have there. That's the working hypothesis, and I want to emphasize that, right? One of the great things is that we've laid out a hypothetical timeline for this asteroid, and I published this back in 2015. We're going to test all of that, right? We're not only going to test it with the asteroid encounter data, but we're going to bring a sample back, and the sample is going to tell that story in great detail.
Okay, I think we're just about out of time, so that will conclude our press conference, and we'll reconvene at 3 o'clock.
Thank you.